this week, we are going to do a type of function called an exponential function. And we'll talk about what that looks like in a moment. But I just wanted to do a quick walk down memory lane to think about the functions we've done so far. Okay, so these are the four types of functions we will have covered by the end. And these are all in paper one traditionally. Okay, so these are paper one functions. There are paper two functions, but they're what we call periodic functions or trig functions. And we'll talk about that in a separate unit. So just to kind of keep those a little bit separate. When we talk about functions, we often talk about their standard form. And so in the straight line, we normally talk about y equals mx plus c, or sometimes we talk about ax plus q. But that just depends on the teacher involved. That is the same thing. This is the gradient, and this is the y-intercept when we come to straight lines. And so it's good just to have a look back every so often. The other thing I want to point out is that sometimes we don't use this notation. So sometimes what we do is we might use what's called the f of x notation. And we might have something like that. Those are all the same things. They're just straight line functions. And if you want to get different types of straight line functions, you would just put values for m and c, a and q, and so on. When we did straight lines, we spoke about how do we, in fact, let me just stop at that point for that one. Then for parabolas, we spoke about functions that look like this, which is the standard form. And we also spoke about the alternate form of a parabola like that, the turning point form. And you can go, but these are the same thing. You can go between these two methods, but sometimes the question will have something like this, and sometimes it'll have something like this. It's important that you don't get overwhelmed by that and know they are the same thing. And in this case, the important bit is the P and Q relates to the turning point. And then last week, we did hyperbolas, and they looked, well, I mean, like this, A over X plus P plus Q. And so that was last week. And what we did was we learned how to draw them. In fact, we did this for all the functions. We learned how to draw them. And we also learned how to find the equation of them when we're given a picture. Now, that's a lot of talking by me to start. I thought it's important that we just have a quick look at that. And I want to ask you, as students in the class, does that all, I mean, for the new students, I know that this is just a little over-the-top recap. You can go back and look at previous videos, but give me a thumbs up if, for those who have been here most of the time, if you feel like that looks familiar to you. And those who feel like, oh my goodness, I'm drowning in symbols, give me a thumbs down. I just want to get a quick feel for what's in the room. And for those students who are new, if you go back and look at the videos, you'll see how we talk about each of these little things as we go. All right. Now, what's also worth looking at is each graph has its own, style, has its own way of presenting. Okay. Now, the thing that I often look at for the hyperbola is that the x is below the line, right? The x is at the bottom there. If we look at the parabola, we look for x to the power of 2. So that's kind of how we know it. And then the straight line is actually quite simple. It just has x to the power of 1 and y to the power of 1. So we need to know how to recognize different functions. The exponential function, if I have to give you, let me give you a simple one first. So a very simple, the simplest exponential function would be something like that. I want to ask the class, what do you think makes exponential function an exponential function? Like, what is its style? What is the thing that makes it belong to the family of? And I want to ask if someone could put their hand up to tell me or put it in the chat. What gets you into the family of exponential functions? If you look at the way I've written this function. What makes it stand out for you? Antantile has given us a little bit of a hint. I like where that's going. Does anybody want to raise their hand and tell me in person? Sometimes that's just a bit quicker. Pop your hand up and we can hear your lovely voices. Annie has given a hint as well. I think Annie's on the right track. Okay. Do we agree with him? All right. So I agree. It turns out that this x over here in exponent, and that's what makes this thing an exponential function. Now, this is what I call a simple exponential function. Obviously, the standard form can do all sorts of things to that, and the standard form looks a bit trickier, but really what we're looking for is we're looking for an x, which is an exponent, and then we have an exponential function. So what does the standard form look like? Well, we could have, what else do we have? Let's have a look. And I don't want to frighten you guys because this looks a bit thing, but the standard form looks like that. And we'll talk about that later in the lesson. But really, the things that you worry about is the A value. The A value will affect the shape. You worry about any numbers in front that can affect the steepness. What do you think the P value does? I'm curious, those students who have been here for a while, what do you think the X plus P does? You might remember its behavior. We've seen P's before. Have a think about what does it affects the shift. Annie, which direction does it shift? Can it shift the graph? Okay, Amakelele, you're right, it's left or right. Now, the P value is left and right. The Q value is going to be up and down. And you'll look this up later in the lesson. Okay, now I've probably made your lives a little bit more cluttered than it needs to be at the beginning, but I thought it was important that we have a look at all the functions we've covered, and then we zoom in on the exponential, but now it's time to focus just on basic exponential functions. So let's talk about a simple increasing exponential function. So I said to you, y equals 2 to the x is an exponential function. And that is actually what's called an increasing exponential function. And I'll show you now why. What do I normally do when I'm first wanting to draw a function? In my previous lessons, I always have like steps. And I'm going to suggest that step 1, step 2, step 3, and maybe step 4, depending on what we need to do. Step 1 is the shape of the graph. Yes, Annie. Yes, yes, yes. If the value over here is a positive, okay, so if A is greater than, well, not even positive, if A is greater than 1, the shape is going to look like this. So I'm going to draw a little thing like that. So it's what we call increasing. If A is greater than 1, and A being this value here, it's going to be increasing. Then the next thing we're going to do is we're going to find the y-intercept. How do we find the y-intercept? Who knows the secret sauce? Yeah, we make x equals 0. And in this scenario, we have 2 to the naught and 2 to the naught. Oh, wait, 2 to the naught is just 1. Oh, that's good. Okay, now we have to talk about the x-intercept. Well, in order to get a x-intercept, you need to make y 0. But this is a little bit sneaky. 0 equals 2 to the x. That's not possible. So just think about it for the moment. If you take a positive number and you raise it to a power, it can never be zero. And so if there can never be a solution, it means that there is no x-intercept. Yes, Naomi, you've done this before. Well done. Okay, now, the other thing that you can also do is an exponential function has what's called an asymptote. Now, in this particular case, the asymptote is not very exciting. It's on the x-axis. And so the asymptote would just be y equals 0. But in future things, you might find it easier to have that asymptote. So let me show you how you draw this. So what I would do if I was drawing this is I know my shape. That's going to help me. I know that I'm going to have a y-intercept. Now, the asymptote is actually, you don't draw this in, but the asymptote is actually along here, y equals 0. And so you may not cross that asymptote. And so your graph is just going to look like that. It may not cross that asymptote line. So there is no exponential function down here. It never gets there. And so we label this as 1, and we can label this graph y equals 2 to the x. And what you notice is this is increasing. Notice how the graph, it's like it's taking off. It's an increasing exponential function. All right. Give me a thumbs up if you followed my 4 steps. Give me a thumbs down if that was confusing or you feel like I've lost you. I'm gonna let you have a go in a moment yourself, but I just want to see if everyone is on board. Okay. Let me zoom in a little bit. Okay, so now I'm going to change it a little bit. I'm going to say, I want you to try and use my 4-step process, but I want you to try and draw for me the following exponential function. So draw for me the following exponential function, and I will take questions, but I want to give you a chance to fly solo first. I know it's exponential because I see my x floating around in the sky here. Aha. Well, I think there is Naomi, you're sort of on the right track, but actually what happens is that 2 to the 0 minus 1, what that's going to mean is that I've got 1 minus 1, which gives me 0, and 0 is a valid number. So, aha, that's the sneaky one. That's why. And then for the x-intercept, okay, this is a bit tricky, but some of you might spot this. This is an exponential equation, and the only way I can solve an exponential equation is if the bases are the same on both sides. So I really want to turn this 1 into a 2. And because I'm a maths teacher, I know that 2 to the naught is 1. And so you can say 2 to the naught is 2 to the x, and so that then x is 0. Now, you actually didn't even have to do that, because once something cuts y at 0, it also automatically cuts x at 0, but it's nice to see that it works out. Okay, so we've done the first 3 steps. You need to think about the 4th step and then ask yourself, can you draw it? What do you think it looks like? So the exponential graph has a horizontal asymptote. And the good news is the asymptote is just going to be, I didn't tell you this, but the asymptote is just this bit over here. It's y equals -1. And that's because the whole graph has been shifted down by 1 unit. Now, it used to be, in the previous example, the asymptote was on the x-axis. But now in this example, it's gone down by 1 unit. So see if you can draw the graph using this information. We just go, so we have a Cartesian plane. And just like with hyperbolas, I start by putting my asymptotes down. And I label my asymptote y equals -1. My intercept is at 0. Oh, now I see why the x and y intercept are the same, because literally it's at 0. And now I have to fit a graph into this. And it may not cross the asymptote. So it just looks like that. And so there's nothing, this graph never gets down here. It never gets there. It just stays above y is equal to -1, and it goes up from there. Okay. Give me a thumbs up if you follow my working out there. Give me a thumbs down if you're feeling a bit unsure. Right. Now, since we've been talking about this graph, I want to sneak in another type of question that we talk about with functions, which is the range. So this exponential function that we've just drawn, it's called y is equal to 2 to the x minus 1. But often in functions, we like to call it something like this, like f of x equals 2 to the x minus 1. Now, this is exactly the same function. It's just much easier for me to say the function f than to say the function y equals 2 to the x minus 1. So I want you guys to try and work out for me what is the range of this exponential function f. Now, range, I'll give you a hint. The range talks about the y values that are defined for the function. So domain is the x values that are defined for a function. The range is the y values that are defined for a function. Can you try and write down what you think is the range for this exponential function that you've just drawn? Pop it in the chat there. There's 2 ways of doing this. You can use interval or set builder notation. Both are fine. I want to suggest that the range is above -1, and it's all the values that are yellow from there, kind of going up. And so using set builder, it would be y is greater than -1, or using interval notation, like with the brackets, I wouldn't have a square bracket. I would have a circular bracket because I can't include the -1. So it's -1, and then I'd go to positive infinity with also a circular bracket. And so that would be my range. Yeah, and we do like to ask, draw the function, then tell me the range, etc., etc. And just to kind of show you talk about the domain, for this particular graph, all values of x are defined. So whether the x value is here and whether all the way to this side, it just keeps going. I didn't ask you that question, but just to kind of throw it in, the domain for this function that we've just done is just x is any real number. It's basically any value of x. As opposed to y is restricted in some way because you cannot go below it's almost like there's a fence and you may not cross that fence. And that's why the range gets a bit more attention, because it actually something is left out, whereas domain, everything is valid. Okay, cool. I think we need to do one more example before our break. So you are going to draw for me the function. We'll make it 3 to the power of x. We'll say it's going to be minus 2. And I'm going to put a 4 in front. So I want you to try and do the 4-step working out process. And then I want you to try and draw that graph for me. And then I'll try and make my graphics tablet a little bit happier with me. I've upset it, so I need to try and convince it I'm... There we go. Now it's working again. So can you draw for me that function there? Cool. Let's go like that too. Yeah, the dot over here is just trying to focus your attention that it's a multiplication. But even if I hadn't written a dot, it would still, if I wrote this, the dot should be there because it gets a bit confusing. Like, is it 43 or something? I'm trying to show you that it's not 43 to the x, it's 4 times 3 to the x minus 2. So yeah, I think I kind of have to have that dot. Yeah. So in order to know the shape of the graph, I'm just going to first look at my A value. And in this case, it's still looking like this. Okay, I've actually chosen an example where it's quite sneaky to get the X value. So I'm going to help you with it because in grade 11, you don't have what's called a logarithm to help you find this, but let's just do what we can. So I get to that point. So 2 over 4 equals, or a half equals 3 to the X. Now, in this particular scenario, it is possible to raise 3 to the power of something and get a half, but you don't have the skills in grade 11 to do that. You'll have to do it in grade 12. So for now, I'm happy for you to leave that out and just sort of approximate where that point is. I will get my calculator in a moment and work it out for you. But let's just go with the asymptote. The asymptote is going to be when y is equal to -2. So asymptote. So because I made this example up on the spot, solving this equation right now it isn't going to be in grade 11 because you don't have the skills, but I will quickly get my calculator and work out. So the base is 3. Yeah. So the answer for X is just going to be negative 0.63. And I will give you that answer because, yeah, you need logarithms in order to kind of get that perfectly. But I want to see the graph. So what will my graph look like? Well, I'm going to put my asymptote in here. And that is going to be y equals -2. And then what was my y-intercept? It was up here. It was 2, and the x, so that was that one. And the x is minus 0.363. So it's going to be on this side, which does make sense. And now when I come along and draw my graph in, it has to go through those 2 points. And so that's why it goes there, but it may not cross that line. And then I must label it. So this is going to be 2, and this is going to be minus 0.63. Okay, that was quite a tricky one. Give me a thumbs up. So how did you get minus 0.63? Kumo, I used some mathematics called logarithms that you only cover in grade 12. So I'm just going to give you that answer for now. You won't be given a question like this in grade 11 in the sense that we will choose the example so that it works out perfectly. So I'm not going to go into that because you do cover it in grade 12, but it won't be covered now. So it won't be a good use of our time if we go down that rabbit hole. I just wanted to get the answer now to show you that it does work. Okay. Cool, everyone. I think you've done really well, and you've done so well that you need to give your brains a break. So let us stand up and let us take a moment to just take care of ourselves. And let's see. Okay, let's start by, just take a nice deep breath. Take another nice deep breath. and then maybe just swing around a little bit. Whatever loosens your body up. So you can shake out your arms, shake out your legs. Just make sure you're standing. That's the main thing. Okay, and then I like to do a shoulder stretch because my shoulders get tense when I'm writing over my computer. Do whatever, if you getting stiff somewhere, stretch that muscle out. I know it sounds silly saying it's hard work sitting at your computer. Our bodies weren't designed for sitting at our computers the whole day, and more, that's the world we inhabit. So we have to, take care of ourselves. All right, now, in order to really have a good second half of the lesson, we need to raise our heart rates. And so what we're going to do is clear some space around you, and we're going to do what's called jumping jacks. And we're just going to do 20, and a jumping jack is just like this. So in 3, 2, 1, let's go. 2, 3, 4, 5, 6, 7, 8, 9, 10, halfway, 11, 12, 13, 15, 16, 17, 18, 19, 20. Ooh. And that should be enough exercise that you've forgotten about maths because your body's more worried about the exercise. And let us do a quick little brain break. So I just want you to see, can you make 24 using those 4 numbers? That's the quick challenge for today. Lesedi, I'm 1.81 meters. That is how tall I am, whatever that means. So Tando has said 5 times 4 plus 5 minus 1. Let's have a look. Femelo, 5 times 4 plus 5 minus 1. So that's 20. And then I get 25 minus 1, and that is 24. Yep, that is it. So Tolo, you could go 5 times 5 minus 1, but then you still have to use the 4. And so with Math 24, you have to use all 4 of the numbers. Okay, cool. Well done, everyone. I think we've had a good break, and we can get back to the lesson that we are doing right now. Okay, so in the second half of the lesson, all I want to do with you is I just want to cover what's called a decreasing exponential function. So how is that different to the first part of the lesson? Well, if we have y equals a half the power of x, how is that different to the graph of y equals 2 to the x that we saw previously? And so I just want to do a quick little example. If the value of the base in the exponential function is greater than 0, so if a is greater than 0 but less than 1, we say it is decreasing. And decreasing exponential functions look like that, look like they're going downhill. And the reason this happens is if you think about like a number like 2 previously, if I go 2 times 2 times 2, I just keep getting bigger and bigger, right? If I times that by 2, I get 16. But something different happens if I multiply a half by itself. If I go a half times a half, I get a quarter. And if I go a half times a half times a half, I get an eighth, which is actually smaller. And so what this function says, it says as x gets bigger, the graph, the value of the graph actually gets smaller, which is a bit weird. Like, so what I'm saying is in this function, the rule says take a half as the base and raise it to the power of x. Now, when the value inside the bracket is a number greater than 1, the moment you multiply something which is greater than 1 by itself, like 2, it just gets bigger and bigger and bigger. But if you multiply something which is a fraction by itself, something different happens. So, for example, if I did this, I get 1/16. And what's happening here is that each time I multiply by a half, it's half the size. It's getting smaller and smaller. And what this means is instead of the shape going upwards or be increasing, we talk about a decreasing exponential function where the shape is going down. Give me a thumbs up if you understand how if the value, if for A is a fraction, the graph has to decrease. Just give me a little thumbs up if you feel like that makes sense. Okay, well, let's see it as an example. So step one, if I was drawing this graph, is I would say it's a decreasing function. Step two, I'd say find the y-intercept. Well, what is the y-intercept going to be in this case? Well, you make x equal to 0. Put in the chat, what is anything to the power of 0? What is my y-intercept going to be? Yeah, it's going to be 1. Okay, what about the x-intercept? Well, in this scenario, I make y0 for the x-intercept. And now the problem is I can't solve this equation. You cannot raise a half to a power and get 0. So there's no x-intercept. And my asymptote is just going to be the same as before. It's going to be y is equal to 0 because there's basically a 0 on the end here. So what does it look like if I draw the graph? Let me do this. Well, first of all, the asymptote would be along the x-axis, so we don't have to draw it. My y-intercept is at 1. There is no x-intercept. And so when I draw this graph, it just looks like that. And it must go through here, which is going to be 1. And then I label my graph a half to the power of x. So this stuff over here, you don't need to worry too much about it. All I was trying to convince you is that when the a value is a fraction, it decreases, not increases. Now, the only way to know for sure if this is going well for you is to test out this process. So I want you to draw me the following exponential graph. It's going to be a third to the power of x minus 2. And I want you to take that 4-step process and I want you to try and draw me the exponential function, a third to the power of x minus 2. Now, remember that the base here is a fraction. And so your question then becomes, okay, what does that do to my shape? And the answer is it's now a decreasing function like that. What's my step? In fact, I'm going to what is my y-intercept going to be? Okay. Give me a thumbs up if you understand how I got -1 for my y-intercept. Give me a thumbs up if you understand how I got -1. Now, when we find the x-intercept, what's going to happen is that I've chosen an example off the top of my head without thinking about whether the x-intercept can be solved using grade 11 methods. I think I might have to help you, but let's just make sure that we follow the process. We get 0 equals 1/3 to the x minus 2. And then we would bring this to the other side. Now, again, I've chosen an example where this type of equation using grade 11 methods, you're going to struggle to find that value, although I can teach you how to do it. How many of you have got a calculator? In fact, I'll teach it to you. I may as well. How many of you have got a calculator nearby? Just say, give me a thumbs up if you've got a calculator nearby. Okay. Look for the button that looks like this on your calculator. There's a button that says log something something. And if you press that button, the number that goes over here in the smaller box over here is the number that is the base. I'm not going to tell you why this works. We're just going to use it for today as a sort of warm-up from a trick. So you put 1/3 into that box, and then the other number that you've got in your question, which is the 2, you put that over here. Okay, so you're basically looking for the button that looks like this on your calculator, and in the big box, you put the number that's by itself, and in the little box, you put the base. And what value do you get if you do that? Tell me what value you get. Pop your number in the chat there. Yeah. You get x is minus 0.63. Fantastic. Now, step 4 says, what is the asymptote? The asymptote is y equals -2. The asymptote for an exponential function is always just this bit at the end here, the q value. Draw me my exponential function now. Draw me my exponential function. Look at you guys learning about logs, just like that. Ask yourself, what process would you follow when you start drawing this graph? There we go. All right. So now I've got these 2 dots. Now I have to figure out what goes through these 2 dots. What shape am I looking for? And I think I know the shape because I decided to be, it's a decreasing exponential function. And so it is going to look like that. And I label my number. This is going to be -1. Oh, let me label it on the other side. So this is going to be -1, and this is going to be minus 0.63. And the equation of my graph is y equals 1/3 to the x minus 2. Okay, so what I am liking about exponential functions, we've got our 4 steps. We have to watch for whether the roller coaster goes up or the roller coaster comes down. But it feels like we're getting the structure absorbed quite nicely. I want to ask you another question. I'm going to call this function that we've just drawn the g of x, and I'm going to say the g of x is equal to 1/3 to the power of x minus 2. I would like to know, what is the range of the function g? Tell me, what is the range of the function g, which is the function I've just drawn here? So we ask ourselves, what does the range have to do with? Range relates to the y values. Yeah? And so if I look at my graph, the range, I can't touch the edge of the field, but I can. All these values here seem valid to me. So it feels like I have to be above the line. So it's going to be y is greater than something, and y has to be greater than minus 2. Or I could write it as minus 2 to positive infinity, like that. And that would be my range of my function. Okay. And again, the domain isn't very exciting with exponentials because the domain will be everything. There's no restriction on the domain. There's only a restriction on the range because you can't go to minus 2 or below. All right. Simone, if you could put the poll out for students so that they can give us some feedback on today's lesson. I think everyone's done very well, especially because I know you're under exam pressure at the moment. And if we look at today, what we learned how to draw increasing exponential functions. We also learned how to draw decreasing exponential functions. And we also did a little bit of a recap of the different types of functions at the very beginning of the lesson. So yeah, I hope that you enjoyed it.